Previously, we dealt with the potential and problems of QD-OLED through several videos. Today's video is about the detailed structure and principle of QD-OLED panel produced by Samsung Display. In particular, we will understand the basic structure of QD-OLED through the latest patent related to Samsung Display's QD-OLED, which was released last month. Furthermore, we will look into the reason why QD-OLED had to choose the 4-stack structure of 1 green and 3 blue instead of the blue 3-stack structure and the reason why the panel production is difficult. Now let's start the tech trip. As explained in the previous video, Samsung's QD-OLED is produced in a 4-stack structure instead of the previously known 3-stack. Since one stack consists of approximately 7 layers, using a 4-stack means that 7 layers of ultra-thin organic material are added, which means that the production process becomes longer and the material consumption increases. And when it competes with white OLED, it inevitably puts it at a disadvantage in terms of price competitiveness. Nevertheless, the reason Samsung Display chose 4-stack may have been its performance differentiation from white OLED. We will explain the reasons in turn from now on. The patent you see is a QD-OLED related patent that Samsung Display applied for in Europe, and was published on April 13 last month. If you look at the contents, this patent is applicable not only to QD-OLED but also to LCD or micro-LED. The most basic fact is that blue light is emitted from the substrate and rises upwards. Since the main concern of this video is QD-OLED, we will assume that blue light emitted from subpixel of blue OLED of 3-stack. The light emitted from the blue OLED has to be converted to red or green depending on the subpixel, so it meets the quantum dot layers of green and red depending on the location. And since blue subpixel does not require color conversion, a separate quantum dot layer is not included. And the quantum dot layer contains a scattering agent that causes strong scattering, and the reason will be explained later. Light passing through the quantum dot layer meets small particles as shown in the patent drawings. These particles have a very low refractive index and selectively reflect blue. On the other hand, the transmittance for green and red is high. This will also be explained later. And finally, the light exits through the color filter layer. As explained in the previous video, the color filter filters out the unconverted blue color or blocks the external light that enters the device from the outside and causes reflection. A simple representation of the structure specified in the patent is as shown on the right side of the screen. From now on, using this expression method, I will explain the principle that Samsung used the 4-stack structure instead of the 3-stack. To explain more simply, let's take one red subpixel as an example among 3 subpixels consisting of red, green, and blue. As shown in the figure, it is the most ideal case that the blue light emitted from the blue OLED of the 3-stack structure is all converted to red by the quantum dot layer. In that case, if only reflection by external light is not taken into account, there is no need for a separate color filter. However, the absorption coefficient of quantum dot is not very large, so blue light leaks out without absorbing all the blue photons and converting them to red. And if you filter the leaking blue light using a color filter, you lose that much in efficiency. The simplest way to solve this problem is to increase the quantum dot concentration inside the QD layer and increase the thickness of the QD layer. As it appears, Samsung is already using it to the maximum without reducing the efficiency. According to the Beer-Lambert law, increasing the thickness of the QD layer can also increase the absorption of blue light. However, if the QD layer becomes too thick, it causes various problems on the device side, so there is a limit. An effective way to increase the absorption of blue photons without increasing the thickness is to add scattering particles to the QD layer. The blue photon enters the QD layer and hits the scattering particles many times until it exits the QD layer and changes its direction, so the same effect as significantly increasing the thickness of the QD layer can be achieved. According to the patent, a low refractive layer made of nanoparticles is introduced along with the introduction of scattering particles. This is the method to convert the blue photon to red as much as possible. Nano-sized low-refractive particles are located between the QD layer and the color filter. The role of this low-refractive nanoparticle layer is to make the blue light with a short wavelength that escapes from the QD to the color filter is reflected back to be absorbed by the QD layer, while the photon converted to red escapes to the color filter layer. In other words, it introduces a layer with selective reflection depending on the wavelength. Through the combination of these methods, most of the blue photons are converted to red, and the unconverted blue is filtered out by the red color filter. But there is another big problem hidden here. The fact is that not all photons converted to red in the QD layer escape to the color filter layer. In other words, when the quantum dot absorbs the blue photon that has entered the QD layer and emits red light, the light emission direction does not maintain the direction the blue photon preceded, but emits light in all directions in space. As a result, half of the re-emitted red photon is directed to the blue OLED having a 3-layer structure, and is absorbed several times by the metal layer forming the intermediate electrode and then comes out again, resulting in a significant loss of efficiency. Here, Samsung display engineers must have put a lot of thought into solving this problem. In a situation where the efficiency reduction is greater than expected, perhaps someone has proposed a 4-layer stack structure with green or red layers added. And as a result of repeated experiments, they must have found that adding a green layer is effective in increasing the in a subpixel of a 4-stack structure with a high-efficiency phosphorescent green layer added, even if all the blue photons emitted from 3 layers are discarded and only green light emitted from 1 additional layer is obtained, the method is relatively more efficient than the blue 3-stack structure. Perhaps, it is thought that the most efficient combination was found among the methods of combining blue OLED and quantum, and through it, an OLED TV with relatively high efficiency, stability, and excellent color gamut was able to be produced. I will end today's video in anticipation of how the contrast ratio and relatively complex production methods mentioned in the previous video can be addressed in the future.